Okay, this first video is going to talk about the intro to carboxylic acids. NMR with carboxylic acids, your hydrogens are going to be very de-shielded, and you'll see that the signal decreases. They're more upfield as you go further away from your carboxylic acid to 13 range, and then your regular signals would be more upfield. Traditionally, your alpha hydrogens are somewhere between the 2 and 2.5 range. For carbon NMR, we're looking very similar in the ranges, somewhere around 180 to 200, similar to what we saw with ketones and aldehydes. First thing, carboxylic acids, based on the name, you can tell that they're very acidic. And so these lower pKa values are going to be decreased, right? Remember, the lower the pKa, the stronger the acid, based on electron withdrawing groups. So this is partly due to an inductive effect, and the more you have, meaning electron withdrawing groups, the lower the pKa will be, and the better the acid. So substituents effects, if we look at these four examples here, you can see that the more chlorines we add closer to the carboxylic acid, we're going to see a lower pKa. The same thing happens if we move it away. So further away, the higher the pKa, we're still in the normal range for a carboxylic acid, somewhere in the 3 to 5 range. But we can see the closer that chlorine gets, the stronger the acid. Here are some other examples of aromatic compounds. You can see how would the acidity of these 5 differ. So the first thing we want to look at is their pKa's. You can see that the pKa's are going down as you go to the right, so the stronger acids would be on the right side. You can look at our other substituents relative to the carboxylic acid. We have 3 nitro groups. The position does matter, and we can make some declarations about what affects the acidity. Most electron withdrawing group. Remember, these are our deactivating compounds, or deactivating substituents that we talked about with electrophilic aromatic substitution. On the reverse side, if you look at our first 2 compounds, you can see that our first one, it has an electron donating group, and that's going to decrease acid strength, raise the pKa. The last thing we can say is orientation. So we can see that ortho and para are going to have a lower pKa, so those are going to be the strongest or result in the lowest acidity. Reactions. We can turn primary alcohols into aldehydes into carboxylic acids. It's tough to stop at that middle step. The reagents we use here are Jones, Na2CO2O7, or potassium permanganate, the most common. So if we looked at this reaction where we had a primary alcohol, we can turn that into a carboxylic acid. Remember, we cannot use PCC, as that will stop just at the aldehyde. Benzylic positions, if we use either of the Jones or the NO4, we actually can turn any R group that has a hydrogen at that benzylic position into a carboxylic acid at that position. So it doesn't matter if there's multiple groups coming off of there, as long as there is a hydrogen in that first position off the ring. Doesn't matter what substituent's on the other side, as long as it's resistant to oxidation, or there's not a hydrogen there, it will not be affected. Organometallics and carbon dioxide can yield carboxylic acids. You can see that very straightforward mechanism, either Grignard or lithium, that's essentially acting as a carbanion, R-, adding to the carbon. You're adding 1 carbon and 2 oxygens. Your acid workup that follows these reactions is going to give your carboxylic acid. So here would be an example of a reaction scheme. We can start with an alkyl halide, add magnesium, get our Grignard reagent, then react it with carbon dioxide, and of course its last step, acid workup. If we had other groups that are susceptible to Grignards, you can also go the nitrile way, using a CN compound. We can still get our carboxylic acid this way using acid or base. And so we could see that if there was another substituent, either a hydroxy group or even a carbonyl group down there, we could then shift just this one position to a carboxylic acid. Substitution addition elimination is the main way we're going to go through mechanisms when working with carboxylic acids and carboxylic acid derivatives. These are the four main ones that we're going to focus on and as we go through in chapter 20. And so we're going to go through two sort of templates for acid and base conditions that are going to make the mechanism proceed the same way. So we'll start with the acid mechanism. First step, we're going to protonate. Remember, we're going to protonate the carboxylic acid, not at the acid portion, but at the carbonyl position. So our carbonyl can come up, pick a hydrogen away, and now we have a protonated oxygen. At this point, we can then have our nucleophile come in. So this is the addition elimination portion of it. Nucleophile comes in, pushes electrons out onto the oxygen. You can have a base, depending on the conditions, come and take away that from the nucleophile. Then the electrons from the oxygen can push back down, having the leaving group leave. And then your last step would be deprotonating that oxygen, dropping that hydrogen down. And again, all dependent on the base based on your conditions and what type of derivative you're dealing with. Base mechanism is going to be very similar. The only thing, we don't need to protonate here, we're in base. So our deprotonation is either going to be a base of our nucleophile, creating our nucleophile. And then same steps too, addition elimination, we've now made a nucleophile that's an anion, so that can go ahead and add on its own, push electrons out onto the oxygen. Our next step will then just be pushing those right back down, causing the leaving group to leave. We're set. The last step for this is regeneration of that base or regeneration of your nucleophile. You can draw this using your leaving group, creating more base or creating more of your anion nucleophile. That's it for workshop 1.